So a quick summary for everyone of astronomy and cosmology, the area I work on, and where we are in 2024. So I'll have a chance to answer some questions, and I'll keep this at a fairly low level, but I'll show you a little bit of the physics along the way. But conceptually, it'll give you a good understanding of some of the work I did for my Nobel Prize, but also where we are right now within cosmology. All right, so let me share my screen, and if I can get this going. You need to, I think, allow me to share my screen. It's disabled on your end.
Just let me see where is the permission. 1 minute. Just let me see. I think the professor can share screen now.
All right, is that working for everyone?
We are not seeing the slides, I think. No, it's okay. 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 We can see.
Okay, right. Now let's see if I can. All right, I can see it works now. Good. All right, so let's just start. In 2024, I'm going to give you the answer, and then we'll go through and unpack how we know this. We know the universe is expanding. We know the universe is between 13 and 14 billion years old. We know that the universe is, as I will describe to you, geometrically flat. And we know that the universe is composed of, by mass fraction, something we call dark energy, 70%, dark matter, 25%, atoms, or often referred to as baryons, 5%, and then small amounts of neutrinos, approximately 0.1%, and photons, 0.05%. So that is the universe as we know it is right now, but let's talk about why we know that. So we got to first start conceptually with the notion that we live in a universe that has a finite age. That is, long ago, before stars and galaxies were formed, something happened. The universe as we know it now was created, and it was expanding. It was expanding in all directions. It was very hot, it was dense, and it cooled as it expanded. And we call that time the Big Bang. Now, we don't really know what a Big Bang is or was. We just know that it occurred about 13 to 14 billion years ago. We often say 13.8 billion years. Turns out it's a little less certain than that because of a certain lack of clarity about how fast the universe is expanding. What we do see 380,000 years after the Big Bang is this image of the whole sky taken at microwaves, known as the cosmic microwave background. And so the structure you see there is real, and I'll talk about that those are actually the imprint of sound waves left over from the Big Bang that percolated across the entire universe for 380,000 years. 380,000 years after the Big Bang, the universe cooled to about 3,000 degrees Kelvin, and the hydrogen atoms suddenly were able to recombine. They grabbed their electron, and electrons have a big cross-section to light for scattering. Hydrogen that's neutral has a much smaller one. So the universe went from being opaque to suddenly clear. And so it was like the fog bank lifted, and we could look back to the fog bank And that's the fog bank left over from the Big Bang. So to go out and explore the universe, we need to start being able to measure things like distances. Fortunately, we have the concept that the further away something is, the fainter it appears. That's the inverse square law for light. We often refer to this as using standard candles. So if we can go through and look at something we think has the same number of watts, we measure how bright it is in terms of watts per square meter, and essentially tells you the distance by using the inverse square law, as Newton figured out. The other thing we have is it turns out we can measure motions. So if a galaxy, for example, of stars is moving away from us, the light that is emitted from it gets Doppler shifted by the motion, and so you could actually measure its velocity. Now, I'll talk a little bit about sometimes there's something else going on besides velocity in the universe, and that will become important. But we go back to the early 20th century, the whole notion of what was going on was not clear, so people were just out measuring things. And Edwin Hubble went out and used data of galaxies, some taken of their spectra that measured the velocity, or redshift, as we like to say, and some about how bright the brightest stars were in the galaxies. So he plotted how fast the galaxies appeared to be moving away, because they were all moving away except for just one or two, and that was a mystery at the time. And he plotted how far away they were by how bright their brightest star was. And so he plotted distance as essentially, something proportional to the square root of the brightness of the stars. And so you can see that he got what is called Hubble's diagram. And the further away something is across the bottom of this diagram, well, the faster the object was moving away, that's the y-axis. And from this, Hubble went out and proclaimed, well, this means that the universe is expanding. And you can kind of understand that by this cartoon. I've just taken the universe and I've expanded it. And if I overlay before and after, you can see that when I've expanded the universe, nearby objects have moved just a little bit, and distant objects, well, they've moved a lot more. Indeed, in an expanding universe, the further away something is, the faster it appears to move away from us. And if you take this to the extreme and do a kind of a thought experiment, if you take the universe and you put it in reverse, then you can imagine everything gets closer and closer and closer to the time of the Big Bang. It's a natural occurrence. If the universe seems to be expanding, that you will naturally get the Big Bang out of it, because as you extrapolate back in the past, things have to get closer, and eventually everything's on top of everything else. All right, so graphically, let's think of what this means. You plot the distance between two galaxies, the universe is expanding, they get further and further apart over time. So if you can measure the slope of that line, which is distance divided by velocity for a galaxy, you can go back in time and you can measure when the Big Bang occurred. So you can figure out how old the universe is. And this is exactly what I did for my PhD thesis back in 1993. Here I'm showing my PhD supervisor at Harvard, Bob Kirshner, how fast I thought the universe was expanding. And the answer that I got was that the universe was about 14 billion years old. That is, if I divided distance divided by velocity for galaxies, the answer was 70 kilometers per second, that's the velocity, per megaparsec, that's a distance. And a megaparsec's just over 3 million light years. Now, let's talk about the theory that underpins this. Einstein's theory of general relativity. Now, this started in 1907 when Einstein had a revelation apocryphally described by him when he saw a person fall off a roof. And as the person presumably fell to some sort of demise, he didn't call an ambulance. He thought, he said, wow, that person wouldn't have felt gravity because the acceleration would have counteracted the force of gravity. And he said, I think that must always be the case. And it took him 8 years to try to reconcile the notion is you can't tell the difference. You're in a rocket ship accelerating at 9.8 meters per second squared, or you're sitting on Earth being accelerated by gravity by 9.8 meters per second squared. They are equivalent. Now, after 8 years, in 1915, he was able to publish his theory, and that theory made a lot of predictions, mainly that space would be curved, and so that if you looked at an eclipse, for example, as Eddington arranged to occur in the eclipse of 1919, that the stars would be displaced because of the curvature of space. And it turns out that it would seem, although may I say there's some dispute about the veracity of Eddington's measurements, that what Einstein predicted was seen in nature. And this is the experiment, believe it or not, that made Einstein famous to the general public. So we think of Einstein being famous because E equals mc squared. Well, that was famous for physicists back in the earliest 20th century. But being able to predict that space was curved in advance, that's what made Einstein famous. So, of course, the theory of relativity stays with us today, and it makes many predictions. And one of the things is that conceptually, you think a little bit differently about the velocity, apparent velocity of galaxies. Rather than them moving away, it's space that's expanding. So imagine you've got a photon traveling to the galaxy. Well, space is expanded. The photon's traveling through space. So the photon gets stretched by the expansion of the universe. So in this diagram, I've just let you watch it again. You've got a photon is stretched, and the bottom one shows you its original size. And so that will, stretching the photon increases its wavelength. And the more stretching of space it travels through, the more the photon is stretched, the redder it becomes. So not the Doppler shift, but rather a redshift due to cosmic expansion. Now, all of this is put together in general relativity in this set of equations. I'm not going to go through it in detail, but you can calculate, because the universe is so well behaved from general relativity, how bright an object's going to appear back in time, or back at how much redshift there was. And it's based on pretty much one or two important things. This diagram has in it the notion of, if you look at the distance on the second line, an object of luminosity L will have an observed flux that depends on the speed of light, the Hubble constant, which is h0, so that's an overall how fast the universe is expanding now. 1 plus z, or 1 plus z, is the redshift. Z is how much space is stretched. And then it turns out this thing of omega k is what the density of every type of material there is in the universe. So you might have photons, you might have atoms, you might have neutrinos, you might have other things. And so each one of those things have a density given by omega. And then that type of material has what we describe as an equation of state, which turns out to be given by the term W. So the W for atoms is 0. For photons, it's minus a third. Dark energy is -1. Neutrinos have a number that's almost 0, but just a little different. So there's a whole range. Photons are plus 1/3. So this is the general equations that we go through, but it allows you to go through and make plots of how things change in time. So imagine you have a universe that has nothing in it. So there is no density of anything no photons, nothing. So it's a really boring universe. Then the universe just keeps going, coasts, gets bigger and bigger over time. So how big the universe is, which we call the scale factor, which is related to the redshift, but it's effectively 1 over the redshift. Over time, the universe just gets bigger and bigger over time. On the other hand, if the universe has stuff in it like atoms, the atoms have gravity, and the gravity slows the universe down over time. So the universe slows down slowly over time, provided that the total density of material is less than a critical value. And if a critical value, this factor omega is equal to 1. If the universe exceeds that critical value of density, then the universe slows down, eventually stops its expansion, and then goes in reverse and ends in what I like to describe, or Douglas Adams like to describe, as the ganab gib. That's the Big Bang backwards. So every universe starts with a Big Bang, but only some of them end in the ganab gib. Now, general relativity tells you that matter curves space. And so if you look at space, and this is a 2-dimensional representation of a 4-dimensional, or sort of a 2D of 3D of what is a 4D space of X, Y, Z, and time. So a universe that has a critical density is flat, but it can have different shapes. If the universe is heavy, then mass and gravity curves the universe into a sphere. If the universe is empty, it's naturally kind of springy and goes away the shape of a hyperbola or a saddle. And then the universe that has exactly the right of matter, well, that's just right. That's flat. And so you can see that triangles look differently in these space. And so in a flat universe, triangles add up to 180 degrees. But in a finite universe, the spherical one, triangles, just like they are on Earth, add up to more than 180 degrees. And in the saddle hyperbola universe, triangles add up to less than 180 degrees. And so that means that we can actually go out cleverly in astronomy and measure triangles. And I'll show you an experiment that allows us to do that later on. All right, so in 1994, I had just finished my PhD, and I pitched to the people here at Mount Stromlo in Australia that I wanted to measure the expansion rate of the universe back in time, because we had ways to, with new technology, to see objects not millions of light years away, but billions of light years in the past. So we could actually see if the universe was changing back in time. And I could see if the universe was slowing down a little bit. And if it was slowing down faster than that yellow line, I knew the universe was finite and heavy and would end in the ganab gib. On the other side of that line, I knew gravity loses the battle for slowing the universe down, and the universe expands forever. So we needed to go and use the new technology and a way of measuring one of the brightest things in the universe, a type 1a supernova. So type 1a supernovae are the explosions of white dwarfs where they detonate as thermonuclear detonations. They produce about 2/3 of the iron in the universe. They take about 20 days to reach maximum light, and then they fade into oblivion. So these things, it turns out, are about 5 billion times brighter than the sun, and we can measure their distance with appropriate calibration to about 7% on per object. But then you can do many of them and kind of use Poisson statistics to go down and measure to much more precise measurements, probably to about 1%. So we put this team together in Chile because it was a Chilean team that figured out how to use these objects accurately. And here we are in Chile talking to Nick Sunseth and Pete Chalice about forming this team to work together. But it was hard because it was 1994. The first big digital cameras were out there. Here is an image from one of the astronomy cameras of the time. It was a 4 megapixel device. Doesn't sound like much now, but there were no digital cameras in the consumer market at this point. And we would take 50 gigabytes of data a night when the largest hard drive that we had access to was a gigabyte. So it was big data back when we didn't have the word big data. And you would have to sift through all this data and find a needle in the haystack. And I'll show you one of these needles. This is a supernova, and we know that because we take 2 images. We had to write, and the stuff I did, write the software that essentially finds these things by subtracting one image from another. And you can see this little bright spot on the left on the 28th of April appeared where it was not there 24 days earlier. This object turned out to be 5 billion light years in distance. So its light took 5 billion years to reach us. It exploded before the Earth was formed. And we would only find 3 or 4 of these a night. Not all of them were useful, so it was hard work. But after about 3.5 years, I'll show you the result, but first let's just look at a movie. Here we are in Chile. This is the 4-meter telescope, Blanco telescope at Cerro Tololo, where we did this work. Here's Nick Sunsef, and he and I are observing at least the first night. You only get a couple nights a year, so every minute counts. And we would be at the telescope making sure all the data were right. And the data would come in, and then we would need to go through and send it through our software. And my software used early neural networks, and we had to find the needles in the haystack. And the neural networks would do the first job, but essentially a bunch of people had to do the rest. And so we would work checking out whether or not it was a glitch, and then we would come up with the candidates, because the next night in Hawaii, on the largest telescope on the planet, still to this day, the Keck telescope, 10-meter telescope, we would go through and have a team, also part of our team, Adam Rees, who won the Nobel Prize, Alex Filipinko from Berkeley, use Keck to identify and get the redshift and make sure it's a type 1a supernova. So after you do this about 20 times over 3 years, lots of hard work, we were able to put essentially how fast the universe was expanding back in time, as I showed you in my little pitch that I made. And this is what we found. You can see in the nearby universe, the objects, you can't really tell where they are on the line, but the distant objects all lie above the line. That is, they're not consistent with the pink gravity wins part. They're not in the gravity loses yellow part. They're above the line where something funny is going on, where the universe has actually not slowed down due to gravity. It's sped up due to gravity. That was a big surprise to us, as you can imagine, in 1998. So we, and then a team from Berkeley led by Saul Perlmutter, who were working independently using a very similar technique, we kind of stumbled on this in 1998 at the same time and published our data showing that the universe seemed to be speeding up. Now, that was a crazy result, and it is a result that is best explained, even to this day, of something that Einstein came up with in his equations. His equation allow a form of matter, which we call dark energy, where it is part of space itself. So as space expands, this stuff is tied to space. So if you double the volume of space, the density of this stuff stays constant. So its energy seems to remain constant. Well, the density of atoms, of course, drops inversely proportional to the volume. Now, if this stuff exists, it causes gravity to actually repel space. And so you get this interesting feature where space will speed up over time because it pushes on itself, and the more space expands, at some level, the more this material can push on itself. And so you get an exponential runaway if the universe is only made of this stuff. So it was a crazy idea that Einstein made up in 1917, although it's kind of allowed in his theory, and he always knew that, to help make the universe not expand at all. Because in 1917, he realized his theory caused space to be in motion, but he didn't know the universe was expanding. He looked around and said the universe shouldn't be in motion. So he thought, well, actually, we could have this, and that could counteract the gravity of everything else, and we could balance the universe out. Turns out it's unstable. So the universe was always going to start expanding or get into motion, so it didn't fix anything. And he often said he was a donkey, is what he actually was quoted as saying. He acted like a donkey, sticking with this concept for a long time. Now, if you go through and do a detailed analysis with that equation I showed you earlier, you find out that the universe is a mix roughly of 30% material that is like atoms or has gravitation like we're used to, and 70% stuff that's pushing on the universe, stuff like dark energy, the cosmological constant. So that's the analysis. Now, 1998, this seemed pretty crazy. People wanted to go look at it in different ways, and they did. But the most compelling experiment came from looking at the cosmic microwave background. But before we get there, let's just remember what this is going to look like from a theoretical point of view. So I showed you this diagram of the graphical representation of the equations. So this, excuse me, this universe we have measured that's accelerating actually looks like that. That the universe starts out slowing down. The universe then speeds up and will exponentially grow forever into the future. And the reason you get it starts slowing down is that the density of atoms and everything else is high right after the Big Bang. And this cosmological constant is, it's got a very low density then. Its density is constant back over time, where the density of atoms and everything else drops over time. And so as the universe expands, it's slowing down. But at some point, we think about 6 billion years ago, the density of the cosmological constant became higher than the density of other forms of material. And so it started pushing the universe apart. And then that, of course, will in the future drive the density of everything else to zero. And its density will always stay the same level it is now, and the universe exponentially expands. So the way that we've really been able to look at the universe in detail is through this cosmic microwave background. So it turns out this is an amazing experiment that cosmology has because it's so precise in our ability to understand and measure it. So as I said, those are sound waves. And it turns out that if you throw a rock into a pond, the wave action depends on what the pond's made out of. If it's honey, it doesn't look the same as if it's water. And so the Big Bang, it turns out, was like throwing a bunch of rocks into a pond. The waves splash around for 380,000 years, and then we get a snapshot of the universe, 380,000 years, when it becomes transparent. And we can compare that wave action to our theoretical models. And these are what the theoretical models look like. It's a complicated set of equations, but they're equations, again, that we understand really, really well, even if they're kind of hard to solve. And so depending on how many atoms or baryons on the left there is, the wave action looks a little different. It turns out if you have matter as atoms or dark matter, non-atoms, so these are things that have gravity but don't interact with each other, then you get a different set of curves. And so you can kind of look at what the universe is made out of, if it's important back at this time. and look to see what the wave action says. So this is the data of the wave action. It tells you, this diagram shows you how many waves are how big the amplitudes of the waves are, so how big the waves are at different scales. And you can see there's a really preferred scale at about 1 degree, but then there's all these other bumps and wiggles, and those are caused by the wave action about what's in the universe, the different types of matter in the universe. Now, the red data, the little error bars are shown, and the curve is the theory. So you can see the curve fits the data really, really well. And it tells you that you need something called dark matter. This is material that has gravity, but as I said, it doesn't interact with anything. It just goes right through itself, goes right through atoms, and otherwise its gravity is the same as an atom. And you need 6.5 times more dark matter than you need atoms. And we, of course, have seen dark matter or evidence of it across the universe since the 1930s. Every time we look at a galaxy, they're spinning faster than the amount of atoms in it. So it's like about 6.5 times the matter is missing. When we see clusters of galaxies go through each other, we can see in pink here, their atoms colliding and producing X-rays, but in the kind of bluey purple, when we look at where their gravity is, because we can see the gravity because of lensing, where the gravity bends space and magnifies things a little bit, or demagnifies it. It appears that most of the mass hasn't slowed down and created X-rays. It's just kind of gone through itself without interacting. So there's lots of reasons to think dark matter is there. We just don't know what dark matter is. We suspect dark matter is a particle, but we keep looking for it and we do not find it. The other thing that the cosmic microwave background does is it allows us to measure how big a triangle is in terms of degrees. And so in the different universes, we know physically, because of the physics is very well known, we know exactly how big those sound waves are. And then we can see how big the sound waves appear on the sky, and we can see the geometry of space, whether or not the universe is spherical, hyperbolic, or flat. And remember, those have a different triangle degrees. And so it's kind of just like, whoops, I'll go back. It's kind of looking like at the back of a spoon, or the other side of a spoon. You can magnify on one side, you demagnify on the other, and you can therefore predict that in the spherical universe, the things are going to be magnified and look bigger than they do in the hyperbolic universe. And so here's what the calculations say. If you have a hyperbolic universe, the sound waves look small. They look much bigger in the spherical universe. When we compare to what we see, the universe is almost exactly flat. I mean, it is really close, 1 part in 1,000 at this point. So the universe kind of when you add up everything in the universe together, it's flat. So when we go out and we try to understand that, we know that compared to that critical density, we have to have 100% of the critical density from everything. We know that, turns out from measurements of the cosmic microwave background, but also from galaxies and other things, that 30% of the critical density has to be stuff that has normal gravity. So we have 70% mystery matter, the same stuff we seem to have discovered in our supernova measurements. And it turns out you can get a little bit of this from these equations, but in the end, no matter which way we look at it, we seem to have a universe that's 70% dark energy, 25% this stuff we call dark matter, and 5% atoms. So the stuff we can see here on Earth is only 5% of the universe. 95% of it is stuff we cannot detect here on Earth. We don't even know how to look for dark energy. Dark matter we keep looking for, and we keep not finding. So the way what we call the standard lambda, which is cosmological constant, CDM, cold dark matter. So lambda CDM is what we call this in physics. Cosmological works is you end up with essentially initial density fluctuations. That's the bumps and wiggles in the early universe. And we think that's due to quantum fluctuations when the universe was insanely dense. It's made up of a whole bunch of stuff: photons, neutrinos, baryons, dark matter, dark energy. The universe, fortunately, appears to about 1 part in 100,000 to be homogeneous on large scales. That is, it's the same everywhere. We have the theory of general relativity, and then we can go through and run this through. We see the universe reionizes due to stars and black holes, probably about 500 million years after the Big Bang. And what you see in the universe is almost exactly in agreement with everything. There's a few little things that are popping up. So Adam Rees, who won the Nobel Prize with me, has demonstrated that the expansion rate in the nearby universe appears to not quite match up with the expansion rate you get from the cosmic microwave background. Now, it's still not absolutely clear. There isn't some problem in the measurement, but it's becoming very, very uncomfortable. They disagree by about 8%. So that 8% might be a complete revision of physics as we know it, or it could be some stupid, dusty junk in the universe we're not keeping track of. But I don't know what's going on there, but I'm becoming very uncomfortable with this problem. So it's a problem to be solved. But we are not done yet, even if that is just an accident rather than real. We don't know what dark matter is. We don't know what dark energy is and why it's there. We don't understand in the standard model of particle physics why neutrinos have mass. We do not understand why the universe is not just full of photons, because right after the Big Bang, the universe should have been composed of equal measures by the standard model of matter and antimatter. And when they come together, they produce photons. What we know is that there are 10 to the 9 photons, so 1 billion photons for every atom. So there's a asymmetry in the equations at 1 part in 10 to the 9 we don't understand. And then I say, what is inflation? So however we look at the universe, we seem to need to have it magnified by 60 orders of magnitude in the first tiniest amount of time after the Big Bang. Now, that being said, the whole notion of what's going on there, we would need to talk for several hours, I think, to truly unpick. So the whole notion of the universe expanding exponentially, it would seem, in its very early time, is something we don't truly understand why or how yet. Of course, we have big astronomy questions as well. We want to understand with the James Webb Space Telescope how the universe has evolved from the Big Bang to the present. And the James Webb Space Telescope and eventually the Square Kilometre Array are showing some surprises. And other things we might want to do, more mundane. Is there life on other planets? And the next generation of extremely large telescopes, coupled with planet finders in space, are going to allow us to look for example, oxygen in exoplanets' atmospheres, which are a biomarker signature. Oxygen doesn't tend to be there without life or something like that present. And then one of the things that we're seeing with the James Webb Space Telescope and through laser interferometry is the universe is full of black holes. There are so many, they are so big, and they are starting in the early universe in a way that just seems to not quite make sense. So there's a lot to go there, and we can actually go through and actually see the shadow of the black hole of a nearby galaxy, M87, and a shadow in our own galaxy. So we know they're really there, and the one in M87 is billions of times the mass of our sun. And with James Webb, we're seeing evidence of those giant black holes very soon after the Big Bang, like within a billion years or even less. And we don't know how you could grow them by any conventional physics. So something's going on there. So it is an exciting time. This is M87 on the left, and one of the James Webb really early black hole candidates. I'd say not completely clear it's real yet, but certainly something to look after. So there is so much to do. So astronomy remains a frontier subject in 2024. But what about our future? Well, we're in a universe that's beginning to exponentially expand. So the future of the universe is going to be dark energy. The more space expands, the more dark energy pushes against gravity, creating even more space and more dark energy relative to atoms. So eventually, the creation of space is going to happen even more quickly than light can travel through it. So compared to that previous diagram, you literally get a universe where photons cannot travel through space fast enough. And so here's a slightly different version of it relative to our other one, that photons will expand to an infinite length and become invisible as they get lost in the expansion of the space. That means that things we see now, we will not be able to see in the future. So unless dark energy suddenly disappears for reasons unknown, the universe will, at an ever-increasing rate, expand, fade away, and cosmologists like me in the distant future will be out of a job because we'll have absolutely nothing left to look at. So make sure you do your work now before it's too late. I'll stop there. Thank you.
Thank you very much, Professor. If we have time, I would like to ask the participants to present one question. And to do that, I will ask to raise a reaction in Zoom and then turn on the microphone, please. There are some questions in YouTube, but I will start here with the Zoom questions. Does anyone have a question? If no one has, I have a question on my own. Okay, so we have one participant that has a question. Santiago Costa. You can talk, Santiago. We are not hearing you, Santiago.
Are you hearing me now?
Yes, yes.
I have a question. What if dark energy, like dark matter, is another thing we make up just to explain what is we observe experimentally. What if the dark energy does not exist in itself? Is this is my
So
question?
I understand what you're asking. Yep. And so that's an interesting question. It gets really down to the foundations of science. So science is about observations and then theory that allows you to make predictions. So in 1998, we showed observations that the universe was accelerating. We demonstrated dark energy could explain what we saw. That then provided a framework for making future predictions. And so when we went and looked at the cosmic microwave background, we saw exactly what was predicted in 1998. And almost every measurement we've made since agrees with that initial prediction. The exception is that when we measure how fast the universe is expanding in the local universe and compare it to the cosmic microwave background, those disagree by 8%. Now, 8% doesn't sound much, but this theory, if it's correct, doesn't make mistakes. So, in the end, you always have theories, you're always testing them, and reality, as we perceive it, is essentially how well a theory predicts something. Now, if you have two theories that predict the same thing, we try to choose the simpler one. That's Occam's razor. But you never really know in science. That's why we always test everything. We don't take anything for granted. And I want you to think about the analogy between Newton's laws and general relativity. We still use Newton's laws. We know they're not right, but we still use them because they're right enough and they're a lot easier than general relativity. So what's real is the idea of force and the way we do things in Newton's right? Nope, but it's right enough. So science is a little complicated, and in the end, it is the numerical calculations of equations and our interpretation, noting we interpret everything with our eyes, our brains, our instruments. That's what is real. So be very careful about what real means. It's more subtle than we give it credit. And remember, magic is when you don't understand, when the reality you thought was real changes something, right? When suddenly you see something that doesn't work the way you think reality should work, that's what we call magic. So by the time you have to figure out what's going on before it become real again. But it's an important question.
Thank you very much.
Does anyone have another question to ask? If not, I would like to ask here with my colleague Helder, that is by my side. I would like to ask Professor if there is a problem with dark energy because our prediction for the value differs from observations, and this causes the two strong sides that are dark energy and modified gravity. I would like to ask Professor if the professor likes more dark energy and dark energy models, or modifications to general relativity.
So I'm very agnostic. All what I care about is can I make a prediction that I can test? All right. So if your modification of gravity were to predict, for example, a discrepancy from the cosmological constant model that we could measure, that would be interesting. But if your modification to gravity is identical in all ways to a cosmological constant, then it's not very interesting because, as I just indicated in the previous question, what's reality? And the cosmological constant is simpler. And so it wins. So we need, even if modified gravity is correct, if there was no way to distinguish it from something else, then you go for the simpler as reality. That's the hard reality. So I know that's not very satisfying, but that's sort of the way we think.
Yeah, thank you. Because I work on modified gravity, and one of the questions I always have is the number of parameters that these theories tend to have, and it's not possible to have such number of parameters that we cannot observe. It's very difficult to test some theories because they have, for example, 40, 50 parameters. It's very hard. And that was my question.
Indeed. And remember, if you've got enough parameters, you can fit anything.
Yeah, exactly. Thank you.
Look at ChatGPT.
Does anyone have more questions?
Well, if not, I hope you guys have a good get together in Lisbon. And I know it's a good active physics community. I have never been to Portugal, but someday hopefully I will be. And so I wish you all the best.
Thank you
And
very much.
please enjoy your next 3 days.
Thank you very much, Professor. Thank you.
All right, take care. Bye-bye.
Goodbye. Thank you very much.